So in today's video, we're going to look at 8.3, which is the standard normal distribution. This is a specific type of normal distribution. And what we're going to do is we're going to look at both probabilities and values, and we're going to see if we can determine those from this particular type of normal distribution. So let's go back to what we did in 8.1 and 8.2 actually. Let's look at our normal distribution curve. Okay, we know it goes off towards infinity and negative infinity at either end, and we know that the mean is right down the middle. Okay, when you have a standard normal distribution, it means that your mean is 0 and your standard deviation is 1. Okay, so for the standard normal distribution, and only for the standard normal distribution, it's when you have a set of data that follows this normal distribution, but not only does it have that bell curve shape, it has a mean of 0 and a standard deviation of 1. Okay, so that means when you draw out this normal distribution curve, the mean of 0 is right down the middle, and then your standard deviation, when you start going either side, and you're plotting out the standard deviations either side, it actually goes to 1, 2, 3, -1, -2, and -3. So on that x-axis, between -1 and 1, they are your x values, okay? Between -1 and 1, you have 68% of your data, okay? And we looked at the probabilities, it's roughly a 0.68 probability that you will land between -1 and 1 in this case, okay? In the same way, you have a 0.95 probability of landing between -2 and 2. So it's the probability that you will have an observation between those two values. And also you will have a 0.997, roughly, chance of landing between -3 and 3, finding an observation that is between -3 and 3. Okay, so the standard normal distribution is just a particular type of normal distribution where you have a mean of 0 and a standard deviation of 1. Okay, so it's slightly different to what we've had before, but it's the simplest type of normal distribution possible. The reason that we like this is actually because we can take any set of data that follows normal distribution, and we can actually do something called a Z transformation. And what that Z transformation does for any set of data that follows normal distribution, it will actually convert that particular set of data so that it has a mean of 0 and a standard deviation of 1. Because as you can imagine, with a mean of 0 and standard deviation of 1, you have the simplest calculations possible. Okay, you don't have to deal with any decimals, you don't have to deal with any big numbers, you are just dealing with the simplest type of distribution possible. So we like this particular standard normal distribution rather than just any other type of normal distribution, because not only does it follow the bell curve, but it has the simplest mean and standard deviation possible. So as you'll see in 8.4, when we look into other normal distributions where you take a data set that again has this bell-shaped curve, but it has a different mean and standard deviation, so it may have a much larger mean and it may have a random standard deviation. What we're going to do later on is do a Z transformation, and a Z transformation just brings it back so that your data set is actually converted to have a mean of 0 and a standard deviation of 1, because of course calculations are much easier when you have it that way. So not only is this called the standard normal distribution, you may also see it called the Z distribution. And that is due to what we're going to do in 8.4, which is a Z transformation, taking any set of data that has a normal distribution and drawing it back so that it has a mean of 0 and standard deviation of 1. And because that is called a Z transformation, we actually call this standard normal distribution the Z distribution, because it has a mean of 0, standard deviation of 1, and by using that Z transformation that we're going to do, we can bring any normal distribution back to this standard normal distribution. Okay, So we saw last time in 8.2 that when you look at a particular normal distribution curve, so let's draw one out here, okay? When you have a normal distribution curve, we look specifically at our empirical rule. So we had our mean was right down the middle, and then we looked at standard deviations either side. So we took the mean plus 1 standard deviation, the mean plus 2 standard deviations, mean plus 3 standard deviations, and you can do the same the other side. Okay? And we said that we already know from the empirical rule that you've got about 68% of your data that lands within 1 standard deviation of the mean, 95% of the data within 2 standard deviations, and 99.7% within 3 standard deviations. So those actually corresponded to the probabilities of landing between those 2 data points, which makes sense because if you've got a certain amount of the data that lies between 2 points, the probability of actually having an outcome, having a data point between those 2 points as an outcome is going to be that percentage. So if you've got 68% of your data between here and here, okay, well, you're going to have a 0.68 chance of having an outcome between those 2 points. So it makes sense when you look at the probabilities. So that probability was the area under the curve between those 2 points. So because we've got 68% of our data between here and here, okay, remember this bell-shaped curve is a histogram, okay? It represents the shape of a histogram where we've got our values on the x-axis and our frequencies that go up on the y-axis, okay? So that bell-shaped curve shows the frequency of particular data points, and that's what forms this bell-shaped curve. So if you've got 68% of your data between here and here, you've got roughly a 0.68 chance, it was actually 0.6826 chance of landing between those 2 points. The annoying part is we do have these probabilities where you land between 2 data points that are a certain number of standard deviations away from the mean. So I can figure out the probability of landing between 2 data points where I'm looking 2 standard deviations either side of the mean. I know the probability of landing between the mean minus 2 standard deviations and the mean plus 2 standard deviations is 0.95 roughly, okay? But what happens if you're trying to find the probability of landing, let's say, between here and here, okay? I've taken 2 completely random values, 2 completely random x values, and I want to find the probability of having an outcome between those 2 values. Well, I'm not a certain number of standard deviations away from the mean here, okay? I'm at 2 completely random values. How can we calculate that probability? Well, we can't use the empirical rule because I'm not a certain number of standard deviations away from the mean. So what do? And the answer is you use a calculator. There is a function for it on the calculator that I'm going to show you. And you can go ahead and use that function and it will calculate that probability for you. So when it calculates the probability, what it's doing is finding the area under that normal distribution curve. In this case, it's a standard normal distribution curve with a mean of 0 and standard deviation of 1. But it's going to find the area under that curve between those 2 points. So if we were looking at these 2 random data points here and here marked in the yellow, what it's going to do to find the probability of landing between those 2 data points is actually just going to find the area between the 2 of them under that curve. Okay? So I'll show you how to do that on a calculator when we go through some examples. The other thing that we might want to do is when we are given a probability and we want to find the value such that we have this certain probability of finding a value that is greater than one particular value or less than one particular value. Let's go ahead and draw this so that we can see what this looks like. So let's say that they give you some particular probability, let's say 60%. Okay, they'll say find the particular value such that we have a probability of 60% of having an outcome that is less than this certain value. So in that case, you are trying to find this particular value such that the probability of being less than this value, so the probability, which is the area under the curve to the left of it, okay, because we want the probability of being less than this certain value is 60%, okay? So you may want to try and find this value given the probability, or it may say to you, okay, let's go and draw this out again. Find a value such that the probability of being greater than this particular value is, let's say, 70%. So you may have to find the particular value such that the probability of being greater than this particular value is, let's say, 70%. So you would have an area of 0.7 under the curve. Okay, so you may have to find a particular value such that you are given the probability of being greater than or less than that particular value. And again, the calculator can do that for you. And we'll go ahead and see how to do that. Because you're going to be doing this thing called a Z transformation in 8.4, and this thing is called a Z distribution because at the moment we are just going to deal with things that have a mean of 0 and a standard deviation of 1. The actual values that you find tend to be denoted by Z. Okay, so when it says to you, find the given value Z such that the probability of being greater than Z is 70% or 0.7. Okay, so you always call those values in a standard normal distribution because you're going to be using a Z transformation later on to bring it back to this standard normal distribution that is also called the Z distribution. We tend to denote values within this distribution as Z. Okay, just as a heads up. So the functions that we are going to use on our calculator are actually found under the distribution menu. So what you're going to do is go to second and vars, this thing that says distribution above it. It was where we found our binomial PDF and binomial CDF. It's in the same menu. But the two functions that we're going to look at today are the normal CDF and inverse norm. So you want options 2 and 3. Let's start with option 2. What option 2 does is normal CDF, and that will tell you the probability of something happening and getting an outcome between two values. So you're going to type in your two Z values, in our case, because we are looking at standard normal distribution with a mean of 0 and standard deviation of 1. You're going to type in your lowest value and your highest value. Okay, so you want to find the probability between that lowest value and the highest value. You want the probability of some outcome between those two values. So for example, we know that we have a roughly 68% chance of being one standard deviation away from the mean, or within that range. Okay, so our Z values in that case were -1 and 1. Now we are dealing with the standard normal distribution. So our mean is 0 and our standard deviation is 1. So that means that we are looking at one standard deviation either side of that mean of 0. So we know that this probability should come out to roughly 0.68. So we know that that's the answer. Let's go ahead and check that. And we see that we get roughly 0.6827 if we round it. Okay. So what this will do is if you type in your lower bound and your upper bound, it will tell you the probability of landing between those 2 points, of finding an outcome between that lowest and highest value. If your calculator does not show up with that menu and you do have an older calculator, you go lower bound, upper bound, mean, standard deviation in that order if you just have to input it in the home screen. Okay, so lower bound, upper bound, mean, standard deviation. Let's go back to our menu, and this time we're going to look at inverse norm. That's the other function that we want. What this will do is if you type in an area, it will give you the value to the right of that area. So if you type in the area that's under the curve, okay, for example, I'm going to put in an area of 0.5, okay? What this will do is it will give me the value to the right of that area. So if you draw out your curve and you have a value on it, this is the area to the left of that value underneath that curve. Now, we're again dealing with a mean of 0 and a standard deviation of 1, okay? That means that 0 is right down the middle. And we know underneath that curve, we have 50% of our data on either side, okay? So I know with an area of 0.5, okay, that 0.5 area is to the left of 0, okay? It's always the area to the left of the value, so the value is to the right of the area. So this should come out to 0 because 0 has an area of 0.5 to the left of it underneath that curve. So let's go ahead and do that. And we get 0 as expected, okay? We're going to go through some examples where you get to use these in different scenarios and they tend to word the problem slightly differently each time. So I'm going to go through that as well. So now that we've done those calculator techniques, let's go ahead and use them on some examples. Okay. The first few examples I'm going to go through are when we are given the particular z values. So you're given either 2 values or 1 value, and we're trying to find the probability of landing between those 2 values or less than or greater than 1 value. Okay, so we're going to look at that. And then after that, we're going to be given the probabilities, and we then need to find the value such that the probability of being greater than or less than a particular value is the given probability. Okay, so let's go ahead and do these. Now, when you are trying to find the probability of being between 2 values or being greater than or less than one particular value, they can phrase it in 2 ways. They can either ask you in terms of finding the area under the curve or finding the probability. Remember, it's the same thing, okay? The area under the curve is the probability, okay? So they can ask it either way, just be aware of that. So in this one, I'm going to say to find the area under the standard normal curve. So remember, it's standard normal. That means that we already know from reading this, because it's a standard normal curve, a standard normal distribution, we already know the mean and standard deviation. We know it's got a mean of 0 and a standard deviation of 1. So whenever you see that word standard normal, we know that we're going for a mean of 0 and a standard deviation of 1. So we want to find the area under the standard normal curve between the values of z is 0 and z is 1. Okay. Now, because we want to do that, again, I always say this to people, whenever you do anything in probabilities or anything in statistics, always draw it out. Okay. It's way easier to see what's going on when you actually draw it out. Okay. Again, because it's a standard normal curve, we know that the mean is 0 and the standard deviation is 1. Okay. So when we go ahead and draw it, we know that the mean of 0 is right down the middle. And when we plot out these standard deviations, okay, then I know that they're just going to be 1, 2, 3, -1, -2, -3. Okay, where roughly from the picture, I should have about 68% of my data between -1 and 1 because my mean is 0, standard deviation is 1. So within 1 standard deviation of the mean, I've got roughly 68% of my data, roughly 95% of my data within 2 standard deviations, and roughly 99.7% of my data within 3 standard deviations. Okay, so I want to find the area under this standard normal curve between z is 0, so between the value of 0 and z is 1. So I want to find the area under the curve between those 2 points. So I'm trying to find that area. Okay. Well, in order to do this, we go to our calculator and we're going to use normal CDF. Okay, normal CDF is always used whenever you're trying to find probabilities. Inverse norm is whenever you're trying to find values, okay? So we have our values, we're trying to find the probability of being between those two values. So we're going to go ahead and use normal CDF, okay? So it always goes lower bound, upper bound, mean, standard deviation, okay? So for those of you with a particular calculator where it doesn't come up with a menu, it always goes lower bound. So our lower bound is our lowest value here, it's 0. Then the upper bound, which is 1. And then our mean, and then our standard deviation. So our mean is 0, our standard deviation is 1. So when you type that into your calculator, it should come out to 0.3413. Now that makes sense, because remember, when we did our empirical rule, we can actually get this value from that as well. When we did our empirical rule, if we go 1 standard deviation either side of the mean, we looked at it in the 8.2 video, 0.6826 was my area under the curve between those two values, which was roughly 68% of my data. So I know that between here and here, the area under the curve between those 2 points was 0.6826, okay? Well, I'm looking at half of that, which is 0.3413. So this value that you get off of your calculator, it actually agrees with that empirical rule that we were looking at. Now the next one I'm going to phrase it in terms of probabilities. So the next one is going to be to compute the probability that a standard, again, we've got that word standard, so we know that we are looking at a mean of 0 and standard deviation of 1. So we've got a standard normal random variable is less than 1.27. Okay, so I want the probability of having a normal distribution for a set of data, and in particular a standard normal distribution for a set of data, and I want to find the probability of having an outcome that is less than 1.27. Okay, again, draw it out for yourself so then you can kind of see whether the value that you get out actually makes sense. Okay, now it's a standard normal random variable, so again I've got a mean of 0 and a standard deviation of 1. So mean of 0 and a standard deviation of 1. Okay, we already know that given that it's a standard normal random variable. And I want the probability that this variable is less than 1.27. So 1.27 lands around here. And because I'm looking for the probability that the random variable is less than 1.27, I want the area under the curve to the left of that value. So I'm looking for the area under the curve to the left of 1.27. Okay. Now, here's where the issue comes up, because we know we're looking for a probability, and so we know that we go ahead and use normal CDF. Okay. Okay, so we know we use normal CDF, but then when we use normal CDF, you always go in the order lower bound, upper bound, mean, standard deviation. Question is, what is our lower bound in this situation? Okay, we said this in 8.2. The x-axis actually goes up to infinity and down to negative infinity. That curve never actually hits the x-axis at any point, okay? You've never got a complete 0 frequency of any value. There is always a probability, even though it may be incredibly small. There is always a possibility that any value can happen, but it may be so incredibly small that we just don't worry about it, okay? But that means we have no technical lower bound here, because if this shoots off towards negative infinity, okay, you can't type negative infinity onto your calculator as your lower bound, because this thing goes off infinitely in the negative direction. So what do we use as a lower bound? Well, we know that we've still got some data to the left of -3, okay, even though it is not a lot, okay? So what we tend to do is, you can do this one of two ways, but one of these ways is sufficient for now. What we tend to do is just to type in a large negative number as a lower bound. In the same way, if we ever need an upper bound, you just type in a very large positive number. So if you need a lower bound, you type in a very large negative number. If you need an upper bound, you're going to type in a very large positive number. When you are dealing with the standard normal distribution, remember we've got a mean of 0 and a standard deviation of 1. We've got the majority of our data within 3 standard deviations of the mean. So we know that the majority of our data is already to the right of -3. Most of our data is already over here. But we do have some data, although it be a very small amount, that lies to the left of that -3. So in a standard normal distribution, if we ever need a lower bound, we tend to use -10. It's very unlikely that you've got any data more than 10 standard deviations away from the mean, okay? You have such an infinitesimal amount, like it's so small that you just don't worry about it, okay? So you are going to catch pretty much every single data point within 10 standard deviations of the mean. So we tend to use -10 as our lower bound if we need one. And if we ever need an upper bound where we don't have one, so let's say instead I was looking at what's the probability of being greater than 1.27. Well, in that case, 1.27 would be a lower bound, and I could then use 10 as my upper bound. So if you ever need a lower bound or an upper bound, use 10 or -10. Okay, so in this case, my lower bound that I'm going to use is -10. And my upper bound, the highest value that I can be at, is 1.27. Okay, so I'm looking at between -10, because I've got some really negative lower bound, and then my upper bound is 1.27. My mean is 0 and my standard deviation is 1, because I'm looking at the standard normal distribution. If you go ahead and type that into your calculator, you're going to get 0.8980. Okay, so the probability of being less than 1.27 is 0.8980. So as I said, if you ever need a lower bound in standard normal distribution, it does not work for any normal distribution. If you've got some other random mean and standard deviation, this will not work. But for the standard normal distribution, if you need a lower bound, use -10. Okay, so that gives you your answer. So we've got a 0.8980 chance of being less than 1.27 in this standard normal distribution case. Let's do a greater than problem. So in this one, we're going to determine the probability that a standard normal random variable is greater than 1.37. Okay. Again, you're going to draw this out. Okay. We know that a mean of 0 is right down the middle because we've got a standard normal random variable. So again, standard normal, I know I've got a mean of 0, standard deviation of 1. So you can go ahead and plot it out roughly, just so you have a quick sketch. Okay, and we want the probability of being greater than 1.37. So 1.37 lies around here. And we want the probability of being greater than it. So we want the area under the curve to the right of 1.37, which is the area under the curve here. Okay. Now in this case, we have our lower bound. The lowest value that I'm taking on here is 1.37. But this time I'm going to need an upper bound. And in the same way that we dealt with a lower bound, as I said to you, having any values that are more than 10 standard deviations away from the mean is pretty much non-existent, okay? We're not going to worry about them. So if I use an upper bound of 10 in this case, bearing in mind my standard deviation is 1, so if I go up to 10, I'm 10 standard deviations away from my mean of 0. So using that upper bound of 10 is good enough in this situation. I'm never going to be more than 10 standard deviations away from the mean, okay? We already know that within 3 standard deviations of the mean, I've got 99.7% of my data. So being more than 10 standard deviations away from the mean is pretty unheard of. So 10 is a good enough upper bound if you ever need one. So again, I'm looking for a probability. I know I'm using normal CDF, okay? Then my lower bound goes first, which is 1.37. The upper bound goes off infinitely, but we're going to use 10 because 10 standard deviations away from the mean is large enough. Mean of 0, standard deviation of 1. Type that into your calculator and you're going to get 0.0853. Okay, so you only have about an 8.5% chance of being greater than 1.37. Okay. The reason I always say to draw these as well is because when you type these into your calculator, you can kind of see if it makes sense from your sketch, okay? If you come back to here, okay, if you ended up with some really, really small probability like 0.1 when you've done this, okay, looking at your diagram, that makes no sense whatsoever, okay? Having around a 90% chance of being less than 1.27 kind of fits with the diagram that you've got. So I would always recommend drawing it. Number 1, to see what your values should be, but number 2, to make sure that your probabilities somewhat match up, okay? It's only got to be a sketch, but it really does help when you actually look at this because this makes sense with the diagram that is drawn. Just as a heads up, another way that you could have done this, and I don't really recommend doing this if you don't have to, but what you could have done here is actually flipped this around, okay? It actually makes it more complicated, but it kind of proves a point to make sure that everyone's on the same page and knows what's happening here, okay? Remember, the area under the curve equals 1. The probability of landing somewhere under the curve is 100% chance, okay? You're always going to land somewhere under this curve. So the area under the curve is 1. So what I could have done here, and again, I don't really recommend it because it's more effort than you need to put in here. But what I could have done is instead said, okay, right, I'm going to do normal CDF. But what I'm going to do is actually find the area under the curve on this side. Okay, again, you probably don't want to do this, but it just proves a point to make sure everyone's on the same page. If I did this and found the area under the curve on that side, my lower bound would have been -10, my upper bound would have been 1.37, my mean would have been 0, and my standard deviation would have been 1, okay? So all I did instead was said, okay, I don't have a lower bound here, I'm going to use -10. I'm going up to 1.37, I've got a mean of 0, standard deviation of 1. That would have given you a value. Then what I could have done is 1 minus that value. So then I could have done 1 minus that value, and it would again come out to that same value of 0.0853. Okay, so you can figure out either side, and then if you need to, do 1 minus it. But by drawing that curve, we already know what our lower bound is going to be, and we can use a particular upper bound. Okay, but if you particularly wanted to and always wanted to do stuff to the left, you could do that and then just do 1 minus it. Okay, it will come out to the same value. Just be aware of that it is completely possible to do it. That way it's just more effort than it's worth. So I would go with this first method that I use down here. Okay, now we've dealt with all the probabilities, I want to look at finding values. So given a probability, can we find the value such that that probability is the probability of being less than or greater than this certain value that we're trying to find? So for this one, we're going to find the value of z such that the area to the left of Z is 0.9147. That's the same thing as saying find the value of Z such that the probability of being less than is 0.9147. Okay, so they can phrase it either in terms of the area or the probability. Okay, again, draw it out. Okay, if we draw this out, we are trying to find the value of Z such that the area to the left of Z is 0.9147. Okay, you're basically saying here that the probability, if you're landing to the left of a particular value, okay, you're trying to find the probability of being less than that value. If it was the area to the right, you would be finding the probability of being greater than that value. Okay, so make sure that you can always put it back in terms of the problem. If they ask about areas, make sure you can do it in terms of actual probabilities. Okay, so the area to the left of Z is 0.9147. Now remember, the area under the whole curve is 1. Okay, so you know that your value isn't going to be somewhere over here. Okay, if the area under the whole curve is 1, and we're trying to find the value such that the area under the curve to the left of that value is 0.9147, well, that's almost 1. Okay, so you know it's not going to lie somewhere over here. You know it's got to be somewhere on this side in order for there to be enough area to the left of that value to be roughly 0.9. Okay, so let's go ahead and put that in. So I know my value's got to be somewhere over here. Remember, if you go down the middle here, okay, you know that your mean is directly down the middle, which means that I've got 50% of my data to the left of it and 50% of my data to the right of it. So your mean of 0 here, okay, has 50% of the data to the left, 50% of the data to the right. So I know I've got to be somewhere on the right-hand side of the mean in order to have 0.9147 area to the left of that particular value. Okay. Just as a heads up again, and I said this before, whenever you see this Z value, okay, whenever they say find the value of Z, you know it's standard normal. You know you've got a mean of 0, standard deviation of 1. They don't use Z for anything other than standard normal, okay? If they are just dealing with some data that has a normal distribution, but it's not standard normal distribution, so it doesn't have a mean of 0 and standard deviation of 1, they tend to use X. But when you're dealing with a particular data set that has a mean of 0 and a standard deviation of 1, they use that Z as representing the value. So whenever you see Z, okay, I'm going to write this down here, we know to use a mean of 0 and a standard deviation of 1, okay? If they ever use X, which will come across in 8.4, then you know that it doesn't necessarily have this mean of 0 and standard deviation of 1. But whenever you see Z, you know it's standard normal, okay? So let's go ahead and draw this out. So again, we're trying to find this value Z such that the area to the left of it under that curve, okay, so the area under here is 0.9147. Okay. Now, you're going to go ahead and use inverse norm. Inverse norm only works, okay, it asks for the area, the mean, and the standard deviation. The area that you plug in has to be to the area to the left of the value that you are trying to find. Okay, so you have to always, whenever you plug in that area, it always has to be the area to the left of the value that you are trying to find. So let's write this out. When using inverse norm, always use the area to the left, okay, big thing here, to the left of the value that you are trying to find. Okay. So remember, normal CDF finds probabilities, inverse norm finds values. Okay, so just again as a heads up, normal CDF means that you're finding probabilities or areas, and inverse norm means that you're finding values. Okay, so here we're trying to find the value of z, so we know that we're using inverse norm, such that the area to the left of that value, so we're already good because we already have that area to the left, so there's no other work to do. So I know that I'm going to use inverse norm, and remember the first value you put in is the area, so the first value that goes in on the calculator is 0.9147. Then you put in the mean, then the standard deviation. So we know we're dealing with standard normal, so it's a mean of 0, standard deviation of 1. Plug that into your calculator. You get 1.37. Okay. So we know, okay, we can actually go backwards on this. Okay. I know now that this value here is 1.37. What does that tell me? Well, it tells me that the probability of being less than 1.37, the probability of having an outcome that is less than 1.37 is 0.9147. I have roughly a 91% chance of finding an outcome that is less than 1.37. That's what this tells me. Okay. Okay, so for our next problem, I'm going to look at finding a value where we are given the area to the right of that value. So we're going to find the value z. So again, you are given z as your variable, so we know that we're in standard normal. Okay, whenever you're given z, we already know we've got a mean of 0 and standard deviation of 1. So we're going to find the value z such that the probability of being greater than z is 0.7. Okay, so probability of being greater than z is 0.7. So let's go ahead and draw this out. Again, I've got my mean of 0 and my standard deviation of 1. So let's go ahead and plot this out. Will look something like that. Okay, so I know that the probability of being greater than this value is 0.7. That means that my area to the right of that value under that curve is 0.7. Okay, I know that the area to the right of 0 is 0.5. Okay, I've got 50% of my data either side of my mean. Okay, so I've got 50% of my data to the right of 0. So I know I've got to be to the left of 0. I've got to be somewhere probably around here. Okay, in order for my area under the curve to the right of that value to be about 0.7. Okay, I'm somewhere over that side. I'm not sure whether I'm going to be greater than or less than -1 yet, but I'm somewhere to the left of 0, so that my area to the right of that value is 0.7. Okay, so now remember, when you use inverse norm and you plug in the area, it always has to be the area to the left of the value z that you are trying to find. So if my area to the right of that value is 0.7, it means that the area to the left of my value is about 0.3, okay, because overall my area is 1 under the curve. So if I've got 0.7 to the right of the value, I've got to have an area of 0.3 under the curve to the left of that value. So when I go ahead and use inverse norm, the area that I plug in is 0.3 because you always have to plug in the area to the left of the value that you are trying to find. My mean is 0 and my standard deviation is 1 because I'm using that z variable, which means it's standard normal. So I know that my mean is 0 and my standard deviation is 1. So if you go ahead and plug that in, it comes out to negative 0.5244. Okay, which makes sense given the diagram. As I said, you're somewhere around that -1 value, but we weren't sure whether we were going to be to the left or the right of it. But we now know it's negative 0.5244, which makes sense given our diagram. Okay. The last problem that I'm going to do is where you are trying to find the value of z again. So we're going to be doing an inverse norm, but they've actually given us 2 values to go by. So we're going to find the value of z. Okay, again, it's z. We know we're in standard normal. Such that the area between zero and z is 0.3665. Okay, again, draw it out. Okay, I'm looking at a z value, so I know that I'm in standard normal. So I know my mean is 0 and my standard deviation is 1. So you can draw a quick sketch for yourself. And I'm trying to find the value of z such that the area between 0 and z is 0.3665. I'm going to assume here that z is positive. Okay, when you go ahead and do this, it should tell you whether z should be positive or negative. I'm going to assume here that z is positive. Okay, but if it said between 0 and this value or between 1 and this value is this amount, okay, always look at the problem because they should tell you whether z is positive or negative if it's not blatantly obvious from what they've told you. Okay, they should tell you whether it's positive or negative. So I'm going to look for the positive value of z such that this is the case. And I want that the area between 0 and that value is 0.3665. I'm going to assume it's around here, somewhere between 1 and 2, okay? We know that between 1 and -1, I've got 68%, which means that between 0 and 1, I'm going to have around 34%, so 0.34 roughly between 0 and 1, and I've got a bit more than that. I've got 0.3665, so it's a bit more than 0.34, so I'm going to be somewhere to the right of 1. I'm just not sure where yet, but I'm trying to find that z value such that the area under the curve between those two values is 0.3665. So I've got a 0.3665 probability of landing between 0 and this value of z. Now, when you go ahead and use inverse norm, again, we have to plug in the area to the left of z. We've got some of this area, but we actually don't have the whole area to the left of z yet, okay? We know that this area here is 0.3665, okay? But we need the rest of the area. We also need this area as well to plug in. We need the whole area to the left of z. So what I have to do, the area to the left of 0, okay, remember 50% of my data lies either side of the mean of 0. So I've got 0.5 is my area to the left of 0, which means in total, my area to the left of z is 0.5 plus 0.3665. So the area that I plug in is 0.8665. My mean is 0 and my standard deviation is 1 because I know I'm looking for a z value which tells me standard normal. So when you go ahead and plug that into your calculator, it comes out to 1.11.